In this tutorial, I'm going to find the eigenvalues of the 3 by 3 matrix, and that is elements 1, 0, 2, 3, 3, 5, 1, 0, 1. By definition, eigenvalues are the roots of the characteristic polynomial. And the characteristic polynomial, which we denote by Pn of lambda, is the determinant of A minus lambda In. In this case, we are given a matrix A, which is a 3 by 3 there. Our In there is the identity matrix, and it will be the same size as the given matrix. So in this case, we would have the identity 3 by 3 matrix. In the formula for the characteristic polynomial there, the identity matrix is being multiplied by a lambda. This will result in having lambda on the diagonal of lambda In there. So we'll be having lambdas on the diagonal, and we are subtracting that matrix lambda In from the matrix A, and it will just result in subtracting lambda from the elements on the diagonal of the given matrix A. So our result there will become the determinant of 1 minus lambda 0, 2, 3, 3 minus lambda 5, 1, 0, 1 minus lambda. And that's the determinant of a 3 by 3 matrix. I usually find it convenient to evaluate that determinant using the row or column with the most number of zeros. In this case, we see that column number 2 there is 2 zeros, so that's the one that I'll use to evaluate that determinant there. So using that column there, I'll be looking at the element 3 minus 1. And you still recall we have the array of positive, negative, positive, negative. We see that 3 minus lambda is sitting on a positive. I'll close the row and the column containing the 3 minus lambda, and still taking into note that it is sitting on a positive, so it will be 3 minus lambda multiplied by the determinant of the uncovered elements. So the result there will be 3 minus lambda multiplied by the determinant of the uncovered elements. And those elements are 1 minus lambda, 2, 1, 1 minus lambda. So we have the determinant of 1 minus lambda, 2, 1, 1 minus lambda. What we are having here is the determinant of a 2 by 2 matrix. And for a 2 by 2 matrix A, B, C, D, its determinant is AD minus BC. So using that formula, we can simplify our characteristic polynomial to 3 minus lambda multiplied by 1 minus lambda times 1 minus lambda minus 2. I can go on and expand this part, and the result we get is minus lambda cubed plus 5 lambda squared minus 5 lambda minus 3. So what we are having there is the characteristic polynomial of the given matrix A is minus lambda cubed plus 5 lambda squared minus 5 lambda minus 3. We said earlier that eigenvalues are roots of the characteristic polynomial. To get these roots, we set Pn of lambda to be equals to 0. So we would have minus lambda cubed plus 5 lambda squared minus 5 lambda minus 3 is equals to 0. I always find it convenient to have the leading term there, the one with the highest power, to be positive. So I will multiply that whole equation by a minus 1, and we have lambda cubed minus 5 lambda squared plus 5 lambda plus 3 is equals to 0. We can now go on and try to find factors by trial and error. So I can try lambda equals to 1. If we put lambda equals to 1, we would have 1 cubed minus 5 times 1 squared plus 5 times 1 plus 3. And it will give us a 4. So we would have a 4 is equals to 0, which is not true. So that will not give us a factor. I'll try a 2. If I try a 2, we would have 2 cubed minus 5 times 2 squared plus 5 times 2 plus 3. Which gives us a 1. So we have 1 is equals to 0, which is not true. So we have not found a factor there. I can try a 3, lambda equals to 3 there. We would have 3 cubed minus 5 times 3 squared plus 5 times 3 plus 3. And it will give us a 0. So we would have 0 is equals to 0. So, and that's true there. So we would have find a factor there. So what we are saying there is lambda minus 3 is a factor. So if lambda minus 3 is a vector, we can then go on and try to find the other vectors using a long division. So I will write my lambda minus 3, which is the vector that we, and that polynomial lambda cubed minus 5 lambda squared plus 5 lambda plus 3. I'll put it under the division sign there. The leading term in that polynomial is a lambda cubed. I divide it by the leading term in the vector that we have, which is a lambda. So lambda cubed divided by lambda, it gives us a lambda squared. So I'll write a lambda squared on top there. Then multiply that lambda squared by lambda minus 3, and we have lambda cubed minus 3 lambda squared. Subtract it from that polynomial, we would have lambda cubed minus lambda cubed, it gives us a 0. Minus 5 lambda squared minus 3 lambda squared. It will give us minus 2 lambda squared, then plus 5 lambda plus 3. And the leading term now there is a minus 2 lambda. Divided by the leading term of the vector there, a lambda, minus 2 lambda squared divided by lambda, it gives us minus 2 lambda. So we'd have minus 2 lambda there. Multiply the minus 2 lambda by lambda minus 3, and we have minus 2 lambda squared plus 6 lambda. Subtract that from the one which is above. We have minus 2 lambda squared minus 2 lambda squared is a 0. 5 lambda minus 6 lambda, it gives us a minus lambda. Then we have that 3, so we have minus lambda plus 3. The leading term now there is a minus lambda. Divided by the leading term of our vector there, the lambda, it gives us a minus 1, so I'll put a minus 1 there. Minus 1 multiplied by lambda minus 3, it will give us minus lambda plus 3. So when you subtract there, it will give us a 0. So we are done with the division. So what it results in is that polynomial lambda cubed minus 5 lambda squared plus 5 lambda plus 3. We can write it as lambda minus 3 multiplied by lambda squared minus 2 lambda minus 1 is equals to 0. So what we have there is we have two components, lambda minus 3 and that quadratic being multiplied and giving us a 0. So if we are multiplying two components and giving us a 0, that means either of them is a 0. So we have lambda minus 3 there is equals to 0. If lambda minus 3 is equals to 0, then lambda is equals to 0. The other option is that this lambda squared minus 2 lambda minus 1 is equals to 0. We can try to find factors, two numbers, which when you multiply them, they give us a minus 1. When we add them, they give us a minus 2. We can't find such numbers, so we can't find any factors. If we can't find any factors, then we use the quadratic formula. So when you are looking at the quadratic formula, the a lambda squared plus b lambda plus c is equals to 0. Compare it with the part that I have highlighted there. We see that our a is equals to 1, the coefficient of lambda. The coefficient of lambda, the b, is equals to minus 2. The constant there is a minus. So using the quadratic formula, we have our lambda is equals to 2 plus or minus the square root of 4 minus 4 times 1 times minus 1 divided by 2. 4 minus 4 times 1 times minus 1, it gives us an 8 there. And the square root of 8, it gives us 2 or root 2. So we have our lambda there will be equals to 2 plus or minus 2 root 2 divided by 2. So those are the roots there. And the 2 plus 2 root 2 divided by 2, when you divide by the 2 there, we'll get 1 plus or minus square root of 2. So our eigenvalues there are the lambda one, which is equals to 3, the one that we obtained. And then the second one there is when we have divided by the 2 there. So we have our lambda 2 is equals to 1 plus square root of 2. And then the third one is when we have the minus sign. Lambda 3 is equals to 1 minus square root of 2. So what you are having there for that given matrix A, which is appearing on the top right hand corner, and the eigenvalues there are lambda 1 equals to 3, lambda 2 equals to 1 plus root 2, lambda 3 equals to 1 minus square root of 2.